After watching this video, you should be able to apply the work energy principle to situations involving changes in mechanical energy. The work energy principle can be expressed using this equation. The total mechanical energy of the body can change if work is done. So if the body has an initial amount of mechanical energy and we do positive work on the body, then the final amount of mechanical energy increases. If the work done on the body is zero, we can see by the equation that the initial total mechanical energy must be equal to the final total mechanical energy. So mechanical energy is conserved provided that there is no work done. If the work done is negative, then we can see that the total mechanical energy of the body will decrease. In using this work energy principle, we remember that the total mechanical energy is the sum of the kinetic, gravitational potential, and elastic potential. We also remember that work done is given by force times distance times the cos of the angle between the force and the distance. In finding the initial and final total mechanical energies, we have to consider the initial and final conditions. The initial conditions will be the initial velocity and the initial height of the body. The final conditions will be the final velocity and the final height of the body. For the purposes of this video, we shall ignore the elastic potential energies. So let's go straight to an example. The question is now up, and you may stop the video to read the question and try to visualize the situation. Once you've done so, continue the video to see the diagram. When solving the question, it's useful to draw a diagram to visualize the situation, showing the initial and the final conditions. It will also be useful to put the data in the diagram. So looking at the question, it states that the car rolls down a distance of 20 meters under the action of a frictional force acting in the opposite direction, of course, 200 newtons, while at the same time falling or losing a height, changing a height of 12 meters. It will therefore be useful to call the initial height 12 meters and the final height at this position 0 meters. The lowest height is usually labeled 0 meters. In solving the question, it will always be useful to expand out the work energy principle as follows. So the sum of the kinetic and gravitational potential energies plus the work done is equal to the sum of the kinetic and gravitational potential energies finally. So all we need to do now is substitute into the equations the unknowns. And the knowns, of course. Okay, so the total mechanical energy initially is found by the kinetic plus gravitational potential. So the kinetic energy initially is 0 because the car is at rest initially. So half mv squared takes the value of 0. But it does have some gravitational potential energy, which is found by the mass, which is 1,000, times g, which we approximate to 10, times the height initially, which is 12 meters. So the substitution is mgh, plus the force, which is the frictional force acting against it, which is 200 newtons, times the distance it's acting for, which is the distance the car rolls down the slope of 20 meters, times the cos of the alpha, and the angle between the force and the displacement is, of course, 180 because they're acting in opposite directions, equals to 1/2 the mass, which we know as 1,000, times the velocity final squared. Now, we don't know the velocity final squared, and in fact, it's the only unknown in our equation. And this is because the gravitational potential energy in the end is taken to be 0 because we have a final reference height of 0 meters. So in working through the mathematics, we have mgh together equals 120,000, fd cos theta together equals minus 4,000, and half mv squared, where v final is unknown, half times 1,000 is 500 v squared. 120,000 plus minus 4,000 is of course 116,000 equals 500 vf squared. Dividing both sides by 500, we get 232 equals v final squared. And so square rooting both sides, we have the final speed to be 15.2 meters per second. The important thing to remember is that the same idea can be used to solve all sorts of problems involving changes in total mechanical energy and work done. We always have to think about what is the initial condition, and therefore, what are the kinetic and gravitational potential energies initially? Is there any work done? Because there may not be any frictional force or anything else that does work on the body. And what is the final condition? And therefore, what is the final gravitational potential and kinetic energies? And then we need to substitute in the expanded form of the equation. You will always get full marks if you state all equations and then substitute carefully in them. Even if you miss out the mathematics, you will only lose 1 mark for this.